Okay, so in the next level of kind of what we're talking about here is this idea of overlap, the Aufbau rule kind of extended. First piece on this is if we go back to the orbital diagram, we kind of have already talked about the pi slice model, how to get long form, how to get noble gases, and how to write the basic electron configuration. We've also talked about the basics of Pauli exclusion principle, Hund's rule, and Aufbau rule. Now we're going to kind of talk about off rule extended, or what happens after about element 19, or technically element 18. If you look back at some of the things that we did last class, in lesson 24, there was a place where I believe it was potassium had kind of a block that was empty. There was an argument or a discussion amongst groups as to whether there should have been a 3D electron on the front side of that page, or whether that was a 4s, and how do we skip and why do we skip, and we're not supposed to skip. Then there also, if you look very carefully at the warm-up we did that day with the two concentric or two identical sets of concentric rings of calcium, there was something kind of mysterious if you looked very careful. The third ring on the third set of rings doesn't have an electron, and there are two electrons sitting on the 4s or the fourth ring. That also brought up a discussion amongst some classes. So we're going to address that today. So we have this Bohr model of the atom, and I've kind of colored the rings different colors for a reason. If we were to take this Bohr model, there's a couple things that Bohr said that we have not talked about. One is that these rings, we kind of imagine them to be evenly spaced, kind of like the rungs on a ladder being perfectly evenly spaced. But that is in fact not what happens according to Bohr. Bohr states that according to his theory, the first energy level is pretty low to the ground, i.e. the nucleus. So if we could imagine this being the nucleus. And then the second ring is, a little bit higher. The third ring, though, the steps are actually getting closer and closer together. Now, this is very, very weird when you think about it, because the rings are getting thicker at the same time that they are getting closer together. So if we were, I'm sorry, I crossed that out, but that's really what is supposed to happen. Yes. So if we were to think about this kind of sideways, what we really have is we have this first ring, we have the second ring, then we have the third ring getting closer, and the fourth ring even closer. And so if you could imagine with your mind's eye, this first ring here is actually, not very thick. The second ring is a little bit thicker because it holds a lot more electrons. It holds 8. The third ring holds 18 electrons, so it should be even bigger, which actually makes there to be an overlap. And then we have the fourth ring that starts here but continues out. And so what we effectively have is we have some parts of the 4s that are actually lower in energy than parts of the 3D. And because we fill from the lowest energy, which happens to be the closest to the nucleus, to the furthest away, we have to fill the 4s before the 3D. Now, if we look at the periodic table, this is kind of transparent, or I should say apparent, because if we look here, this is our 3s, this is our 3p. We haven't even touched this D section yet. Then we fill the 4s, and this is the 3D. So effectively, the D section, the numbers are actually one behind the row, but we'll talk about that later. So this kind of has some ramifications. One, we're going to make sure we fill that 4s before we fill the 3D. And so when we are drawing our electron configuration, it's going to look a little bit different than we expected. It will kind of look our pi slice. If you wanted to do a pi slice, after we get past element 18, I don't require pi slices. So you look like this is your nucleus. This is your, we would say, this is your energy level. This is your sub-level. This is your max electrons. So we've discussed that you're going to fill that one ring first. The first ring has a 1, an S, and a 2. The second ring has two parts, as a 2, S, 2. and then a 2p2. The third ring has 3 parts. It has a 3s2, then a 3p6, and then it has a 3d. The 3d is a little bit further away, and in between there we have the 4s2. Now, just take it for what it is at the moment, that this is what it is. Don't try to make sense of it. Don't try, why is the 4s come for 3D? Why is it called D? Just know that the Aufbau rule states that that's just the way it is. So I'm going to color these for you so you can kind of see how they kind of all stack up. And now we're going to place our 19 electrons on and come up with an electron configuration. So our 19, 1, 2, we're full. 3, 4, full. Oh, this is actually a 6 here. Sorry for that error. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So our electron configuration for potassium, don't forget the brackets and the equal sign, is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay? So this is the ones from the pink ring, the ones from the green ring, the ones from the purple ring, and then we have the yellow ring. Noble gas configuration. If I look at where potassium is on the periodic table, it's here. So the noble gas before it is going to be argon. So it's going to be argon 18, and then what's left? Turns out that argon 18 ends here at the 3p6. So you have potassium 19 is going to be equal to argon 18 plus 4s1. And if you're trying to figure out what's going on here, because you missed something, Google noble gas electron configuration, but also notice that all of this is the same as this. Okay? And if you go back to your earlier pie slices, you should be able to see that. So let's talk orbital diagram. So if you were to draw the full orbital diagram out, so we're going back to this here, the s's have 1 orbital. So then I have 2s, which has 1 orbital. Have 2p, which has 3 orbitals. 3s, which has 1 orbital. 3p, which has 3 orbitals. And 4s. Make sure you leave about a fingertip worth of room between each one. Or, for clarification purposes, go ahead and put the extra line in. And now we're going to fill these up. So you had 19 electrons, okay? I'm going to fill it up, then I'm going to talk about it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Done. Okay? Now, some things that you can observe. 1, we are starting with the first electron in each orbital going up. We fill 1 orbital before we move on to the next. So I filled 1s. I said orbital, but it's really sublevel. We fill 1 sublevel before moving on to the next sublevel, before moving on to the next sublevel, before moving on to the next sublevel, so on and so on. Hund's rule, we are making sure that we put 1 in each one before we double up, okay? And so we have this as our beautiful orbital diagram. So your homework for last night. Your homework for last night was to finish up that worksheet that you received in class. That was the first thing that you did. And the worksheet that you should have picked up says POGL electron configuration. The top has Model 2. Model 2 is not anything for you to do. So your first thing that you need to do starts at question number 6, which is at the bottom of the page. It is very easy. Don't let the look of the model trick you into believing that you don't have the ability to do this, because everybody can. So that's the first piece. The second thing you needed to do was to go back to all of the problems that you did before and to add in orbital diagrams. So at this point, you should have a set of pie slices. You should have a set of all those pie slices should have a long form configuration. Then you should have gone back and added a noble gas configuration. Some of you just got this information on the class that you missed. And then you also needed to add an orbital diagram. As far as your orbital diagrams, what I told you was that you only had to draw past the noble gas. So if this is your noble gas configuration here, argon 18, you could just do the 4s1. You don't have to do all of these, but for some of you, it may benefit you to start from the beginning. So if you're doing this, you don't know how to, if you're doing, just this part and you don't know how to do it, go back and do it all and it'll make more sense because it directly corresponds to these rings. So if you look, this has 2 just like that one. This has 2 just like this one. This is 6 just like this one. This one has 2, the purple one, first purple, just like that one. This one has 6 just like this one. And this one has 1 just like this one. So these are just different ways of expressing the same information. Pauli exclusion principle kind of extended talks about the fact that all electrons rather, should have 4 separate quantum numbers. And those 4 separate quantum numbers are energy level, sublevel, orbital, and spin. So we already know about energy level and sublevel prior to this. Orbitals, that's the number of beds, the number of separations. S has 1, P has 3, D has 5, F has 7. Each orbital holds 2 electrons. So that's where you're getting the 2, 6, 10, and 14 from. And then spin is just the thing that 1 electron points up and 1 electron points down. Again, these are referred to as the 4 quantum numbers. And I know that sounds weird because they don't seem like numbers, they seem like words. But in upper levels of chemistry, these actually get converted into numbers. And if you want more information about that, I'm happy to share it with you. But it is not necessary for this class, and it's not necessary for you to master this information. So I hope this helps as a review to what you missed in class, or if you just need to see it one more time and to go over it again and to move a little bit more slowly and be ready to go. Next class, I guess. Make sure you complete the whisk that is due by tomorrow. And there will also be a new whisk posted as well coming soon. Okay, thanks so much. Have a great weekend. Bye-bye.